Okay, so after you have graphed the tangent function, and you should have something on your paper that shows, or in Desmos that shows you what that tangent function looks like. I want you to go ahead and answer these questions. So hopefully you've already done so. You're just coming to kind of check your work. So the first thing it says is describe the domain and range of the tangent function. Now this is quite interesting because the range ends up being all real numbers. So, a lot of ways you can write that, but what I'm trying to teach you this year for domain and range is to write them in interval notation. So this would be how you would write all real numbers from negative infinity to positive infinity. But the domain. So the domain of the tangent function is quite interesting because you'll notice for sure that pi over 2 doesn't work. But then you probably noticed some other ones did not work also, like 3 pi over 2. So what you're going to notice is that there's these asymptotes that are going to occur at some multiples of like pi over 2. So what does that look like? So hopefully you're noticing that these asymptotes are happening at stuff like, so I'm going to write out here for a second, x cannot equal 90 degrees or 270 degrees. And if you looked kind of backwards, you would also see stuff like negative 90, negative 270. So we have all of these values. It looks like starting at 90, every 180 degrees, you're going to have something that doesn't work in your function. So we can say that our domain, and we can't write this without writing a whole bunch of intervals. So what I'm going to do for this one is say x cannot be 90 plus 180 times some number. I'm going to call it k. Now, I don't have to pick k. I could pick a different number. I think sometimes you might see n or something else of that nature. But what I did, I picked k. And what that means is that some number times 180, if we add that to 90, we're going to get an asymptote. Now, we could also write this as x cannot be pi over 2 plus pi times k. So there's a couple ways you could write that, either in degrees or radians. So describe any special points or asymptotes. Well, we have x-intercepts. We already kind of described our asymptotes. Our asymptotes, we'll do that here, is that x equals 90 plus 180 times k, or x equals pi over 2 plus pi times k. And then our x-intercepts are going to be any multiples of pi. If you look at your graph, you have x-intercepts at 0 pi, at 0, I did that the wrong way, pi 0, at 2 pi 0, at 3 pi 0, and so on. So our x-intercepts happen at pi plus pi times k. So depending on how you want to write that, it's just any multiple of k. And really, I mean, we could have just written that as just x-intercepts are just at pi times k. And k can be anything. K can be a positive or a negative number, and that'll make sure that we include our intercepts that are less than 0. Is there symmetry? Yeah, I mean, there's definitely some symmetry there. It's called origin symmetry or rotational symmetry. So I would say yes, there is origin or rotational symmetry, depending on how you want to write it. And you could be a little more descriptive there. But each of those individual curves has symmetry. But it's rotational. It's not just a reflection over the x-axis, a reflection over the y-axis. How is it different? Hopefully you came up with a few different ways. It's different. It does have asymptotes. Your domain is not all real numbers like it is with your sine and cosine graph. It's not continuous. There's those breaks in the graph. And then why do you think that the tangent graph has asymptotes? And the reason for that is you're going to get some undefined values in your function, right? So when you do anything over 0, if you try to do 1 over 0, that is undefined. And that's what's going to happen when you try to do the tangent of, say, pi over 2. Because remember, that's the sine of pi over 2 over the cosine of pi over 2, which is just 1 divided by 0. So anytime you get something undefined, that's when you're going to see those asymptotes occurring.